Okay. So this work is done by Nisha, Rani, Mahato. So she was not able to come because of visa problems. So I will try to do my best to explain what she has done. So it's about the localization of a group of robots using matrix contractors. So I will try to introduce the classical contractors first, and after explain what we mean by matrix contractors. So a classical contractor, it's an operator which contract blocks with respect to a set, and without removing any point inside the set. So here is the definition of a contractor associated with the set X. So to build contractors, most of the time we use interval analysis techniques. So I will not explain this. So now, what we call by matrix contractor, it's just an extension of this. So you have, as an input of a matrix contractor, interval matrices, and several interval matrices as an output. You return also a list of matrices. So here I write if as the output of the contractor I have A1, B1, and so on, so by the square we mean interval matrices, we still have the contraction and the completeness. So it means that since the contractor is associated to constraints on A, B, C, and so on, I should have the contraction, but also if matrices A, B, and so on belong to the initial interval matrices, they should belong also to the contracted matrices. So it's classical interval contractor, but as an element, I may have several interval matrices. So why it is important? It is important because when we work with a robotics application, we have matrices naturally, and we have also constraints on matrices. So a typical one is a unary constraints. So what I call unary constraint here, because you only have S1 as which is involved in the constraint. So for instance, if I say that S is a symmetric matrix, then the associated contractor, which is minimal, is this one. So for instance, if I have a matrix inside this interval matrix, and if I know that this matrix is symmetric, then using this operation, so I take the same matrix and I make the intersection with this transpose, I will obtain the contracted matrix, and it will contain all possible symmetric matrices that are inside the initial interval matrix. Okay. So it was a simple example, but we can do this for other matrix constraints, such as A plus B equal to C. The corresponding minimal matrix contractor is this one. Oh. I have also some very other important constraints, such as the multiplication, which is a ternary constraint because A, B, and C, 3, or the unary constraint, this one, which say that R is a rotation matrix. For this type of matrix, which are important for our application, at the moment we don't have efficient contractors for this type of constraints. Okay. It would be important to have them, but we don't have them, probably because it's not so easy. And computing the minimal contractor for this would be an NPR problem. Okay. Another example is the contractor associated to a matrix is positive semi-definite. So in this case, since the set of positive semi-definite matrices is convex, there exists some convex methods such as LMI method, which makes us possible to contract optimally an interval matrix with respect to these constraints to be positive semi-definite. Okay, so it was just to give examples, but in the application I will consider here, it will be different. It will be related to interval angle. So I put this as a question because we had the same problem with Nassim this morning, especially because angles, as like quaternion, has a structure which is not Euclidean but more Riemannian. So the set of angles is not a lattice. So let me recall an angle. An angle is not a lattice because it's impossible for me to say that an angle is smaller than another one. So a lattice means that I need a order relation to say that one element is smaller than another one, and it's not possible for the angle. I will explain this later. And in this case, we can generalize interval on what we can call a bisectable abstract domain. So if we want to make interval algorithm as general as possible, what we need. And the idea is to generalize interval algorithm on Riemannian manifold. So what is a Riemannian manifold? I give an example of a Riemannian manifold, which is a clamp bottle. You can see here. It's a manifold of dimension 2, because when you move on the surface, so without inside and outside, it's well known. So it's of dimension 2. And we can use some kind of paving algorithm to search on this type of manifold. So what we can see here is not a variety on dimension 2, it's what we call an immersion. But probably you can see this point, which is here. It corresponds to two different points. So the one which is on the circle, you can see here. On the immersion in R3, they correspond to two different elements. It means when I move, because of the representation. So in this case, how can we do to define interval is this kind of things where we cannot say that an element is smaller than another one. So to apply interval algorithm, we need first to have, so in the Riemannian manifold, you are able to define the distance between 2 points A and B. So the distance will correspond to the smallest distance you can get from A to B using a path in the manifold. Okay, so as soon as we are able to define the distance, we are able to define the diameter, and we'll need this to define what we call generalization of boxes. So we call it here a BAD, which means bisectable, because we need to bisect them, and abstract domain, which corresponds to boxes. So what we need to generalize these boxes? First, we need to have what we call a Moore family. So what is a Moore family? Boxes corresponds to a Moore family because when I take boxes, if I intersect two boxes, I still obtain boxes. Even if the number of boxes is infinite, if I intersect them, I always obtain boxes. So when I say a Moore family, it's not our Moore of the father of interval. It is this Moore, so which defines this kind of Moore family. So we need boxes are Moore family. We also need to generalize interval algorithm bisectors. So bisector is something which takes two elements of this Moore family and is able to generate two other, let's say, boxes or bad bisectable subdomains, such that A and B, the generated bad, do not overlap. A and B cover X, of course, and minimize the max of the width of A and B. The width is defined because of the distance is defined in the Riemannian manifold. So it's okay. So now when we work with angles or quaternion or things like this, we have this kind of Riemannian manifold, and to understand this, I propose to solve how we can solve this equation. And I know that alpha is an angle. So alpha is not an element of R, it is an angle. So when I mean by angle, it means that 0 is the same angle as 2 pi, or the same angles as minus 2 pi, and so on. So this equation, when alpha is an angle, has a unique solution. And we can write it, not so many one, by alpha equal to 2 pi p with k belong to z. Okay. Now what I said is that angles like, okay, is a Riemannian manifold, and usually if we want to use interval method, we have to use an embedding. So it's like an immersion, as I showed before, but which will be injected. So I represent an angle, so it means that here I represent an angle as a point in the trigonometric circle, and if I have an uncertain angle like this, which would be an interval of angle, I could represent in R2, whereas the set of angles is correspond to this. I can represent by a box. Okay. And since R2 is a lattice with, I can define boxes, lower bound, upper bound. But now, if I try to solve algorithms in R2, so in the cos sine space, or if you prefer, in the complex space, then I will add some pessimism here and here, which makes me less efficient. So it's not what we call a wrapping effect, but it is what we call here, I can call an embedding effect. So if you add this, you are less efficient, and it is better to bisect on this space with bisection and so on. Okay. Okay, so that's what I explained here. The embedding effect is explained. So how it works, we can use in the cos sine space, and how it can work. I can represent an angle by its cos and sine, and applying a trigonometric reduction, I can compute the cos and sine of the sum, and to get some interval resolution in the cos sine space. Okay. So just an example, if we want to solve this, and we don't want to avoid, and we want to avoid the 2 pi problem, so modulo 2 pi problem, how I do? I take A and B, I will transform A and B because they are angles, I know that they are angles inside this arc, let's say, and then I replace immediately by their cos and sine. I apply the trigonometric relation in a forward and backward, and I will obtain, after backward step, the resolution. So here it works quite perfectly, just to show that with angles we can live inside the embedded space. So it works quite well, but you have pessimism. If I define this relation, so angles, how it can define rigorously, I first need an equivalence relation to say that if alpha and beta are equal modulo 2 pi, okay, it means that they correspond to the same angles. So in fact, the set of angles is a quotient between R and this relation, which can be written as this one, as I said before, like in the plain bottom. I have a Riemannian manifold. I cannot say that this angle is smaller than another one because of the circle. And then, so how we can do is to be efficient, to work on the trigonometric space. So in this case, we can define arcs which may correspond to some kind of interval inside the circle, and an arc may be represented by its center and by a radius. And the radius is inside 0 pi. So I define a set of arcs, but if I intersect two arcs, the problem is not more valid. For instance, if I take this arc, and if I intersect this arc by this arc, the intersection is not an arc, but a union of arcs. So the smallest, more family, which enclose the arcs, is a union of arcs, and I can define intersection, union, and so on. But it's dangerous to work like this. So even if I have a more family, what happened, is as shown by Chakaverty in his PhD, if you perform propagation on union of arcs or union of intervals, you may have an explosion. And so it's better not to use this kind of union of arcs. Okay, just to explain, so in fact, we work on this, but we will impose, to avoid any problem like this, we will impose that all arcs we consider have width, a radius, which is, so the radius is smaller than pi divided by 2. So in this case, we will not have this kind of problem. It's a way to avoid the problem, to be fast, but the number of problems we solve is small. Okay. So the problem we are interested with is a localization problem. So we have several robots, and the localization problem is to find from measurements, angle measurement, and so on, to compute x1, x2, so the coordinate of the robot. But it is what we call the absolute localization. But in many applications, as the one we have underwater, several robots, they can see, you can see your neighbor can see other neighbors and so on, but there is no possibility to have absolute localization, no GPS system, no landmarks, and so on. So we can only build a relative localization, and the measurement we can do is the angles most of the time and distances. So here we will focus on azimuth. Azimuth means if the north is there, if I see a robot there, then the azimuth corresponds to this angle. So the bearing corresponds to an angle with respect to your heading. So if the north is here, but if I go in this direction, the heading corresponds to the angle between my heading and so the bearing between my heading and where I see the robot. Okay, so it is represented here. You have azimuth angles. Each robot is able to know some information about the other robots. So it's azimuth angles. And these angles are obtained by a compass. You need a compass because of the north, but you also need some goniometric sensor, so angle sensor. And angle sensor could be a camera. Camera gives you an angle. Okay, so we built an azimuth contractor. So we define what is an azimuth matrix. It's a matrix of azimuth where the robot number I is able to see the robot number J. Okay, and on the diagonal, difficult to define it by convention, we take 0. And it is this kind of matrix is inside a Riemannian manifold. Okay. So we present another form of interval, but not exactly an interval because of the problem I explained before, and it is not a new family and so on, but all angles we are assumed to be smaller than are not too large. So we take some relation, some classical relation on triangle. I will not explain them now, but not so difficult to explain from a picture. And we have, if A is an azimuth matrix, then we can show, using triangle representation, that we have this kind of relation where it means equal modulo to pi. From this, we are able to build azimuth contractor in order to have a better approximation of the geometry of the robot. Okay. Also, it's important to build another contractor, which is called a distance contractor, but it's not like the angles. We don't have this kind of singularities we have on the angles. So if a distance matrix corresponds to a specific matrix, which is symmetric, and tells you that the distance, each entry of the matrix tells you the distance between the robot I and the robot J. So, in fact, the distance matrix can be transformed into constraints, and here you have the triangular inequality, the fact that it is a matrix which is symmetric, but also constraints could be or should be taken into account to have better contraction. Okay. So now we may find also some combination between distance and azimuth, taking, for instance, if I know that the distance matrix D is consistent with the azimuth matrix A, if I have this kind of relation, but other relation could also be found. Okay. So I will use this kind of contraction in order to improve the geometry, the geometry of the group of robots. Well, first, I consider 5 robots, and each of these 5 robots is able to measure distances and azimuth, and due to the uncertainty, all these this matrices correspond to interval matrices, and you can see that they are quite small. All of them are small, so because of what I said before, that's what I assume. But even in our application, even if the robots are far, when they are just near to you, you can see with a good accuracy thanks to the cameras. But when they are far, you have some information about where they are due to the sound, and you know where the sound comes from. But it's a bad approximation. But it's less than pi approximation. It's not too large. So the distance matrix most of the time is due to ultrasound. With the sound, you can get the distance between 2 robots. And then we can contract to this matrix, but maybe with some graphical explanation. I have here robots that are represented by the point, the 5 robots, so it's a red point, and the azimuth is represented by the art, but it's not so easy to see them in the picture. But, okay, but here probably this is before contraction. You get a view of what happened. And this is one contraction with respect to azimuth, and we go up to the fixed point. And then when we do the fixed point is here, and when we do the distance, we have a better also approximation because we go up to the fixed point. Many after come back to the azimuth and so on. And with 12 robots, I will show an example with 12 robots where you can, so it's difficult to see because superposition of many sets. So before contraction and after contraction. Okay, so here it was, in the future, of course, it would be nice to work with arts that are larger, a radius larger than p divided by 2. It would be nice. And okay, I finished my presentation.
Thank you very much.
Have you tried some other instruments like the repetition of items?
No, I think we should try. Maybe the work was more on azimuth and bearing. But on distances, it would be, for example, if it is planar, you may have some other constraints of if you know the dimension and it is the case because we know either we are on a plane or we are at least on a 3D space, then you have some other constraints that should be taken into account. But the problem is that these constraints are probably non-convex, so they are not so easy to take into account. So we don't know. Yeah, you can.
I mean, if I understood well, all the setup that you present, the final goal is to integrate the information of all the sensors all together. All the sensors all together. I mean, each robot has a sub sensor.
Yes.
And then
Yes.
you take into account all
Yes.
these sensors all together.
Yes, because what the objective
The
is we have several robots and we want them to have a formation. They need to be at a specific place with respect to the other. For instance, to build some kind of to have a specific shape, triangle, square, and so on. So it is important to know the geometry of the group. But since you don't have GPS system, you cannot have absolute localization. So the idea is to represent the geometry of the group with respect to matrix distances or angle matrices. Okay. So the geometry is represented by this kind of matrices, and after with uncertainty, and we contract these intervals better to have with respect to the constraints we have between azimuth and
But then
distance.
it's a single, let's say, constraint problem altogether.
Yes, we all together.
Altogether.
Yes.
Your question, you, as soon as I understand, you have created a kind of intervals on the circle.
Yes.
Then you have extended this to the torus.
Yes, exactly. Exactly.
This is what you have done.
It is what is written. Whoops, sorry.
N-dimensional torus.
Yes.
N-square dimensional torus. So this is a torus.
Yes, if you want, yes. It is a torus.
Okay.
It is a torus. Yes.
But now my question is, do you think it's possible to? I've heard what you said about unbaited manifolds. I think it's a bad idea to use unbaited manifolds because of the unbaiting effect.
Yes.
That it would be really nice to have a way to always create intervals on manifolds.
Yes, but it's not possible because a manifold, a Riemannian manifold, is not a lattice. It's impossible. You need order relation.
Yes, but you could manifolds. There's two ways to define manifolds. You can do it by unbaited, but you can also do it by curves or charts. So you have a map from this path.
Yes.
And another map from this path.
So you think that I have no idea how to do it.
I think that you did what you have to do. It's just to divide the circle into subparts such that you can define intervals. And this is how manifolds can be defined. Locally, manifold is just Rn, locally.
Yes, I agree.
So here you have divided the circle into two parts, which are segments.
Yes, you create some singularities. No, if you.
No, there is no singularities. There is just two parts. They overlap.
Yes. Okay. Yes, you overlap, and after.
And after you have to create intervals on the green part and also intervals on the red part.
Yes. But when you will intersect them, you will generate two. No. You will generate.
Yes, this is what you really want. To do have this exponential.
Yes.
I think it would be not possible to have all.
I think so.
But it would be really important, especially for robotics, to have a way to dissect S03.
Yes.
The set of matrices, the orthogonal matrices.
Some other comment? No? So thank you.
Thank you.